All right, so here we have an example where we're going to be calculating the magnetic force from a current carrying wire loop. Let's take a look at the problem and the configuration. So here we have the following configuration where we have a wire loop in the YZ plane, where we have a equilateral triangle as our loop. Each side has a value of A. We're also given this B field, or this magnetic field here, that is K times the quantity A minus Z in X hat. So we know that our B field is pointing out of the screen at us for this problem, okay? Now, the model that we're going to use is going to be that the magnetic force is going to equal a steady current I, and for the sake of this problem, we're going to assume this is a steady current I times the integral dl crossed B. So this is really easy, really simply just a line integral problem at the end of the day. And we can break this up into each of these components of this line integral. So we're going to have the force from the bottom plus the force from the right hand diagonal, and then we're going to have the force from the left sided diagonal going back down, and we're going to have to calculate each one of these individually, or will we? In fact, these ones we can actually evaluate via symmetry, and we'll get to that later on, or we can simplify the evaluation with symmetry. So let's do the bottom first. So we're going to examine the bottom. And when we're examining the bottom here, we're going to follow the same model like we did before. The force on the bottom is going to be our steady current I times the integral of dl crossed with our B field, okay? If we go back to our configuration, we have dl pointing in positive y hat, okay? We have it pointing in positive y hat, so we're going to be crossing y hat into x hat. We're going to have a positive y hat, a positive x hat. That's going to result in a negative z hat. So we know that, all right? So let's plug everything in that we know. Let's take care of our minus sign right away and just stick it out in front so we don't forget about it. So it's going to be a negative sign times our constant current I times the integral evaluated on bound 0 to A, because we're going that full length of that first path, A across, and then it's just going to be K A minus Z dy. Okay, now you might be wondering, well, we have a z in here. The simple thing with this is that since we're in the YZ plane, and for this bottom path, we're not changing at all in z. And in fact, we can just fix z to the value we're at, which is 0. So we can just sub in z equals 0, and we end up getting minus I k times the integral on bound 0 to A of A dy, and I forgot my z hat up here, and we should stick that z hat up there so that we know which direction we're going in. We can evaluate this integral pretty easily to get that the force from this bottom path of our loop is minus I k a squared z hat. All right, and so this we need to keep track of and remember for when we add everything back up. All right, let's jump over to our diagonals. So for our diagonals, we should be able to evaluate them one at a time. So for the left, we're going to have I times the integral on bounds A per 2 to 0 of dl crossed B. And then for our force on the right, we're going to have the same thing, but our integral is now on bounds of A to A on 2 of dl crossed B. But one of the things that we can take advantage of here is we can take advantage of the fact that both of these should result in the same thing in the same direction. All right, they're more or less both going in the same direction, and they're more or less both symmetrical. So we can take advantage of this geometric symmetry here, and we can drastically simplify the math that we have to do so that we are only evaluating one integral and just multiplying it by 2. So let's do that. Okay, when we do that, we're going to get that the force from the left and the right is equal to 2I on bounds integral of 0 to a on 2, because both of them in y, as far as we know, are going on a on 2. We know that our dl is just going to be y, and so we're going to get a dl crossed our B field. Okay? We can sub everything in, and then we can take care of our directionality. So we get 2i, not pi, 2i times the integral on 0 to a per 2 k a minus z dy, and now we're crossing our B field, which is in x hat, into what is effectively negative y, because we're moving back from y equals a over here to y equals 0. So we're moving in minus y. So we really are crossing a minus y hat into an x hat. That's, of course, going to result in a positive z hat. Now we can take this guy and evaluate it. I forgot my hat. Now, fair word of warning from me. You can evaluate both of these two integrals up here, this guy, and just add them together, and you should still get the same exact result. In fact, when I originally did this problem, that is what I ended up doing. All right, but when we take advantage of our geometry and symmetry here, we can drastically simplify the amount of math that we have to do, so we can just evaluate one of these integrals here rather than having to evaluate two integrals on different bounds. It just doesn't make any sense. I'd much rather choose this method than evaluating both of these two individually. All right, so let's take what we got from the last part. Force from the left and the right is equal to our steady current I times 2I, actually, because of symmetry, on bound 0 to a on 2 times k a minus z dy in z hat. But here's the problem. You might notice that we have this z term, and now we're actually changing in z. Okay? We're actually changing in z along this dashed line right here. Okay? And so what we need to do is we need to find z as a function of y. Okay? Well, because we know that this is an equilateral triangle, we know that the sum of all our angles of a triangle have to equal pi. Okay? Because it's a triangle, we have three angles. One angle is going to result in pi on 3. So we can effectively say that theta is equal to pi on 3. If we look back at our picture and we set theta equal to just one of these, theta is pi on 3. All right, if we take the sine of our angle theta to get our z value, we're going to get root 3 on 2. Okay, so from here, if we use sine theta, we're going to get square root of 3 divided by 2. Okay, now if you were using this method here, where you were using these two individual integrals, you would use z equals root 3 on 2y. But since we're doing two of these, because we're going to be going up and then back down, we can multiply this function right here, or we can multiply this value by 2 and just get root 3. Okay, so that makes z as a function of y, root 3 y. Okay, and we can sub that in for z now, so let's take care of that. So we have the force from the right and the left is equal to 2I times the integral on bounds 0 to a per 2 times k a minus root 3y dy z hat. And now from here, we can just begin evaluating our integral. So let's do that really quickly here. When we evaluate, we're going to get a 2ik times the quantity ay minus root 3 per 2y squared 0 to a per 2 z hat. We can plug in the bounds that we're evaluating on, and we're going to end up getting I k a squared minus I k a squared root 3 per 4 z hat. Okay, now all we need to do is just add all our forces together. So here's what we have for the right and the left. We got the bottom earlier. Let's add them up, and then we will have our magnetic force. So our total force, our total magnetic force, so F mag, I can't even write mag, geez, mag is equal to the force from the bottom plus the force of our combined right and left integrals. So let's add these up. We're going to get a minus I k a squared z hat plus I k a squared minus I k a squared root 3 on 4 z hat. Pretty simply, we can see that this term and this term are going to cancel out. So our magnetic force for this configuration is just going to be minus I k a squared times root 3 per 4 z hat. All right, fantastic. That is how you find the magnetic force from a current carrying wire loop. If any questions, feel free to leave them in the comment section down below, and I'll do my best to answer them, provided I see them in a timely fashion.